Recursion is one of those topics that sounds simple when you hear the definition, but feels confusing the moment you try to follow the code. That confusion is normal, and it comes from mixing two different ideas that recursion quietly combines. At its core, recursion is a way of defining a problem using smaller versions of the same problem. That's it. Nothing about computers yet, just the idea that to solve a big case, you assume you can solve a smaller case and then build the answer from that. To make this work, every recursive definition needs two pieces. First, a base case, a smallest version of the problem that you can answer immediately. Second, a rule that reduces the problem, so each step moves closer to that base case. Without both, recursion never ends. Now, when we turn that idea into code, it becomes a function that calls itself. That's where the confusion usually starts. Seeing a function name inside its own body feels circular, like the function is asking itself for help forever. But the key detail is that it never calls itself with the same input. Each call works on a smaller input, and eventually one call hits the base case and stops. A clean example is factorial. 0 factorial is defined as 1. For any positive number n factorial is n times the factorial of n minus 1. That definition maps directly to code. If n is 0, return 1. Otherwise, return n times factorial of n minus 1. What actually happens at runtime is a two-phase process. When you call factorial of 4, the program can't finish right away. It needs factorial of 3, so it pauses and calls that. Factorial of 3 needs factorial of 2, so it pauses again. This keeps going until factorial of 0 returns 1. Only then does the program unwind. Each paused call wakes up, multiplies its number, and returns a result to the call above it. Recursion goes down, then it comes back up. That pause and resume behavior is one major reason recursion is hard to trace. Each function call has its own local variables, all waiting on the call below it. The computer keeps track of this using the call stack, the same mechanism used for any function call. Recursion just uses it repeatedly. Another reason recursion feels difficult is cognitive load. With a loop, you usually track one set of variables changing over time. With recursion, there are many versions of the same variables at different depths, plus unfinished work waiting to happen. Trying to simulate all of that in your head quickly becomes overwhelming. This is why experienced programmers use a leap of faith. When writing or reading recursive code, you assume the recursive call correctly solves the smaller problem. You don't trace every call unless you're debugging. This mindset is closely related to mathematical induction. Prove the base case, assume the smaller case works, and focus only on how to combine the result. Recursion isn't arbitrary. It naturally matches problems that are defined recursively. Trees are the classic example. A tree is a node whose children are themselves trees. So processing a tree often looks like handle the current node, then recursively handle each child. In these cases, recursion mirrors the structure of the data. That said, recursion isn't always the best tool. Deep recursion can overflow the call stack. Naive recursion can also be slow when it repeats the same work, like the classic recursive Fibonacci function. Techniques like mnemoization or switching to iteration can fix those issues. The most useful mental model is to separate two layers. One layer is the idea layer, solving a problem by reducing it to smaller versions. The other is the execution layer, function calls being paused and resumed on the call stack. Recursion feels confusing when those layers blur together. Once you keep them separate, recursion stops being magic. It's just smaller problems, a clear stopping point, and deferred work that finishes on the way back up.